Good evening viewers, and once again we are on the journey of learning convex optimization. So, if you remember what we did in the previous lecture was the following, is that we looked at we are trying to look into an optimality condition of this form, and we were also looking into a very general optimization problem where you have both inequality constants as well as equality constants. Now, we have shown the standard optimality condition can now be used expressing the sum rule, used through the sum rule of subdifferentials can be expressed in this form. So, once you can express it in this form, the question is to compute this one and to compute this one. So, we had earlier computed this one, where you see why there is an use of the separation theorem, and then we are now going to compute the case for C1, that is when when I have inequality constants, what would happen. So, in this case we will need here we will need the status condition, that is there exists x hat such that g I of x hat is strictly less than 0 for all I. So, now how do I compute it? So, any v which is in this set, sorry, C1, essentially solves the following minimization problem: minimize minus of Vx such that x is element of C. But come on, we are essentially we want to find an optimality conditions, so that we cannot use an optimization problem itself to figure out how to solve the how to compute the normal cone. So, it is very important that we do it without the help of optimization problems. So, let us see how can we do it in a more straightforward fashion. Now, let us see how I would think if I am possibly getting it as an open problem. You know, it is very important that you think as if this problem has been given to you and you are trying to solve it, and that is the only way one can imbibe the spirit of doing research. And so, here how do I think about it? Okay, I have constraints and all of these are convex. Now, consider those i's which are in I x bar, that is in the active index set, that is the set of all i's for which g I x bar is 0. Then convexity would give me for each I this fact. This is something which you already know. It will give you this fact, and then because I is in I x bar, this is 0, and so for x in C, what I would have is that clear for each I g I x is of course less than equal to 0 and this is 0. Now, take any lambda I greater than equal to 0, I belonging to I x bar. So, that would imply that I am multiply all of these equations by lambda, all of these inequalities by lambda I, then add them up, then I will have Now, does this ring a bell? Of course, it does, because x was arbitrary element in C. So, what I get is exactly something like a definition of the normal cone. So, what does it show? That this thing, this immediately implies that summation lambda I is an element of the normal cone to C at x bar. So, I know that any element where lambda is greater than or equal to 0 and is of this form must belong to the normal cone. So, the question that arises is that for this particular formation of C1, that is set of all x such that Gix is less than or equal to 0, does every element V is of this form? That is, I am asking the following question: is the set of all V in Rn for which V is expressed as so any V that you express like this, where you can vary the lambda i's, my query is this the actual expression? I know that this thing is a subset of this thing, but is the opposite true? That is the question. Now, the first steps are following. So, which we will now do one by one. Let me call this set S as this is S, right. Now, this set V can also be expressed in the following way, following equivalent way. Obviously, for all I. So, it means that either I can write it like this, or I can free up this thing and write the sum from 1 to m with the criteria, this sort of complementary slackness criteria, whichever way you want, or more of a shorthand is of this, that instead of putting this V, you directly write elements of this form. Now, you know very well that this normal cone is a convex cone, and which is by definition which that is true, it is a closed convex cone actually. Now, the question is whether this is also a closed convex cone. So, first step is we will show that S is a closed convex cone under the Slater constant qualification, which we have said earlier that there exists x hat such that G I x hat is strictly less than 0 for all I. So, we are trying to figure out this question. Now, we will do it step by step. Now, when we want to do it step by step, let us look into this fact that it is a cone. The S is a cone is a very simple proof. And what about its being convex? So, S is a convex set would be given as a homework. So, take two elements of this form and show that the convex combination is also in S. Is a convex cone, that is, now we have to show that S is a convex set. Now, this would be homework. How to show that S is closed? This brings us to the question of polyhedral cones. So, let me remind you what is a polyhedral set. So, polyhedral set is a convex set which can be represented as an intersection of finite number of half spaces. So, this can be represented as an intersection now. Okay. So, a polyhedral set usually would look like this, a polyhedral set P. So, it is something like this, you have a half space here, you have a half space here, you have a half space here, it could be a set like this. This is a polyhedral set. Now, if I put all B I equal to 0, that is if I have this set P hat, this k can vary, obviously it does not mean there is some fixed number k. So, this is called a polyhedral cone. There is all of such half spaces have 0 as one of their element. For example, I take this one and I take this one. I just bother about this part, bother about this part. So, I just bother about something above this, whatever. So, I can get a polyhedral set. This is a polyhedral cone. This is a polyhedral cone. So, examples of polyhedral cone, important cones are, look at this thing R2 plus, it is this and this. So, this half space and this half space. So, R2 plus an example of a polyhedral cone, and thus Rn plus is polyhedral. You can make out your own examples of polyhedral cones. Suppose you take in order to just draw this line passing through the origin and take this part. This is also a polyhedral cone. Now, what is important is that you should know this following fact, that polyhedral cone can be represented in a nice fashion. Now, there was another definition of a cone which is called a finitely generated cone, that is you have certain generators, that is you have some fixed vectors say a I, say 1 to k, and create all elements of this form. So, suppose I take in 2 dimension, I take say 2 vectors. There is no condition of linear independence, dependence or anything on these vectors, they are just few given vectors. So, I say suppose I take these 2 vectors in R2. Now, any point satisfying this, that is I multiply with a non-negative number, something like this and add them up, it will come here. And so, any point here, so any point of this form would be within these 2 boundaries. So, given these 2 vectors which I can call A1 and A2, this is the finitely generated cone generated by the generators A1 and A2. So, these AIs are called generators of the cone. And this cone is called finitely generated cone. One of the most powerful results in convex analysis or convex geometry is the following. It says that a polyhedral cone, or rather a polyhedral cone is finitely generated and finitely generated cone is polyhedral. In another way of telling is this, which is more erudite in the sense that it is stated almost in if and only if terms. A convex cone is polyhedral if and only if it is finitely generated. Now, if you look at the set S, which is given in this way, this set is a finitely generated set, where the set of generators are this gradient vectors. This is a set of generators of the cone S. Now, if you go back and look at the definition of a polyhedral cone, this one, then it is clear that a polyhedral cone is closed. And so, here, because this set is every finitely generated set is polyhedral, every finitely generated set is closed. So, this set S is finitely generated through these generators, and is thus closed. So, the 3 requirements, S is a cone is done, which you can show, the convex cone would be your homework, and S is closed because of this polyhedrality. The 3 things we have done has been now completed. Now, our question is to now show this, whether this is equal to this. Now, how do we do this? So, in order to do this, we have to observe this fact that what we have shown is that S is a subset of, and now what we have to show is that NC to show NC x bar is a subset of S. So, the idea is to start with a contradiction. So, these sort of arguments that I will be arguing now is quite common in convex analysis and convex optimization. So, it is imperative that you listen very carefully to the arguments that I will go through. even those who are not from a mathematical background, I will tell them to be very careful and try to argue, look at the argument carefully. So, what you learn, what you are learning is modern optimization, and here analysis plays a very fundamental role, because at the end a lot of problems in analysis was developed, lot of issues in analysis or ideas in analysis were developed to take care of problems in optimization, and thus analysis plays a fundamental role in understanding optimization problems. So, now let me say that okay, on the contrary, let this not be true. That is, I am telling okay, let me assume that what we are guessing is not true. Now, if this is not true, then what would happen? So, there exists a V in NC x bar, means every element in V is not an element here. If it is so, then this will be a subset. So, there must be a V in NC x bar such that V does not belong to S. We have proved that S is a closed convex cone and hence a closed convex set, and thus it is important for us to go back and look at the separation theorems that we have learned, and now we are going to apply the separation theorems. So, application of the separation theorem will lead to the following, and let us see how this is done. So, what we are going to show that okay, V is not in S. So, by the strict separation principle or strict separation theorem, we can show that there exists W not equal to 0 such that W of xi is an element in this set is less than equal to 0 is strictly greater than of course, this S is depending on x bar, which I am not mentioning because we have just taken a fixed x bar and we are working. So, S of course depends on x bar, it is very maybe it is more perfect to put S of x bar. So, I am just so this is what you have from the separation theorem. Now, see let us see where we go. Now, which means my W of xi, which is this is less than equal to 0 for all lambda I greater than equal to 0 and I belonging to I x bar. This is what you have straight away. What does this show me? This shows me the following. So, for the fixed set of indices, for whatever lambda I greater than equal to 0 you take, this sum must always be negative. So, this would immediately allow us to conclude, this would lead to the fact We have really not used Slater condition anywhere, but we will soon use Slater condition, and that is exactly what I am going to show you. Now, let me consider this set K, which is a set of all u in Rn. Now, you can show that K is non-empty. Now, this will be your homework to show that K is non-empty. And the hint for doing this homework is you please use the Slater condition. So, use the Slater constant qualification is the required guideline to do this fact. Now, if this is non-empty, which shows that for this should be u. Once this x bar is fixed, this is a series of convex inequalities actually. This is a series of convex inequalities, and what I have showed that for this series of convex inequalities a Slater type condition is actually holding. So, what you can actually show that closure of K is equal to so this would also be homework, and this the hint is same, apply the Slater condition now, because this is non-empty, the Slater condition is satisfied for this particular set K. And this for this system of inequalities, and if I take this system of inequalities, then the Slater condition is actually satisfied. Then the closure of this sort of set, that is this, and the interior of this sort of set is this. So, this is also homework. So, that would I am giving quite a number of homework, because these sort of practice is very important for you to have an understanding of the subject. If you do not practice in this manner, you cannot understand a subject, mathematical subject like this. The only way to understand a mathematical subject is to solve problems, or try to fill in the gaps in your understanding, fill in the gaps in the theory which you feel by working them out, and that is very important. Now, if you observe that what does this mean? So, if you have a u in K, this would imply by the very definition of the derivative and use of Taylor's theorem, I will have for all I would be having this. This is the meaning of this statement, for all I belonging to I x bar. Now, what does this mean? That when lambda is sufficiently small, then for every I so what happens, because the limit is strictly less than 0, that is the strictly negative point, after some value of lambda, this differential quotient will be strictly negative. That is the meaning of convergence of a sequence. So, or convergence as per se, the very notion of a limit. So, for lambda sufficiently small, I would like to warn the students that those who do not want to follow this proof and feel it is intimidating them, especially engineering students in our country. So, please do not follow the proof, accept this story. This is true when Slater holds. So, this fact is true and Slater condition holds. Just accept this fact for the moment. So, for lambda sufficiently small, so greater than 0 and sufficiently small, what do I have? I have the following. This will be, because I this is 0, g I x bar plus lambda u would be strictly less than 0. Now, because for those I which is not in I x bar, for them g I x bar is strictly less than 0. Then by continuity of those g i's, you can get a lambda sufficiently small such that g I x bar plus lambda u would be strictly less than 0. So, for lambda sufficiently small, I can show this is true for all I equal to 1 to m. So, once I know this, it will immediately tell me that x bar plus lambda u is element of my set C1. Lambda is strictly greater than 0. So, u is an element of 1 by lambda times the set C1 minus x bar. So, this sort of set is of course subset of the cone or the convex cone in this case generated by the set C minus x bar, which is again naturally a subset of the closure of the cone. Now, what do I show where W belongs to? Now, by our explanation here, this W is belonging to the closure of K. So, W belongs to the closure of this set K. So, C1 sorry. Now, since W belongs to the closure of K, one has to note something, that is the following, that what is the closure of K? So, I take any u in K, that u, for any u I take in K, this is what is happening, right. So, naturally if u is in the cone of this, then the closure of K. So, what I am finding is that K is a subset of the cone this. From these two equations, I actually have that K is the subset of the cone of C1 minus x bar. So, this would imply that closure of K is subset of closure of cone of C1 minus x bar. So, this would imply that W is an element of the closure of the cone C1 minus x bar. Now, since W is an element of this and V is an element of this, take any V. So, take, but my V, this V was in the normal cone, but it was not in the set S. So, since V is in this set, V times x minus x bar is less than equal to 0 for all x in C. But this implies that V times W is also less than equal to C or W dash for all W dash in the closure of the cone generated by C1 minus x bar. It is natural because you multiply by some lambda. So, that will be in the cone of C1 minus x bar and you take the closure of, that is you construct, take an element of the closure. So, elements of the form lambda n x n minus x bar would be going to that point. So, then once you pass on to the limit, then you will get this expression, that is okay. Let me see what happens. So, take z element of closure of cone of C1 minus x bar. So, there exists Zn in the cone of C1 minus x bar such that the sequence Zn is converging to Z. Now, Zn can be expressed as some lambda n, because in the cone of this x n minus x bar, right. Now, since C is closed, where C is where x n is element of C, where since C is closed, now if x n converges, now I am telling Z n is converging to Z. So, x n must converge. Since C is closed, if x n converges, it will converge to some element in the set. So, what does this mean from here? What I get from here? I get immediately from this expression V of x n minus x bar is less than equal to 0, which would immediately tell me V of lambda n x n minus x bar less than equal to 0. So, V of Z n would be less than equal to 0, and if I pass on to the limit Z is going to this. So, V of Z is less than equal to 0. So, what I have showed that for any V element of n c x bar, V of Z is less than equal to 0 for all V element of the closure of the cone generated by C1 minus x bar. I do not need this concept. So, here I use the fact that x n is in C, use the definition that V is in the normal cone, then multiply by lambda and it will give me this. As I pass on to the limit, I will have this. So, for any Z, sorry not V, any Z in the closure of Z, which is an element of the closure of the cone of C1 minus x bar, Vz is holding, Vz is less than equal to 0. So, V of W, so what I get here is that V of W is less than equal to 0, naturally, because W I have shown to be in the closure of cone of C1 minus x bar. But let me go back a while and see what does the separation theorem give me. The separation theorem gives me that V of W is strictly greater than 0 for that particular V which we had taken, and thus here we have a contradiction, but we had proved, but separation theorem gave us so that is a contradiction. So, we do not, so what we have assumed is not true, and thus n c x bar is a subset of S under Slater. So, which means n c x bar is equal to S under Slater CQ, n c 1 x bar. So, the optimality condition, this can now be written as so we have already proved that this is image of A transpose, where C2 is nothing but Ax, capital Ax equal to B, set of all x such that capital X equal to B. So, this will give me, so there would exist lambda I greater than equal to 0, where I is in I x bar, and y element of R k, just I have to go back and check what was my Ax equal to B is in R k, right. So, for y in R k we have 0 is equal to grad f x bar plus summation. So, I must have an element V from this, an element from the image of A transpose such that 0 is equal to grad f x bar plus that element from S plus that element from image of A transpose. So, what does an element of S look like? It looks like lambda I grad g I x bar, I varying over I x bar. So, that is exactly what I am writing down. So, or we can write choose if we set lambda I is equal to 0 for I not element of I x bar, then the optimality condition is the following: the Karush-Kuntakar conditions, the necessary and sufficient condition, necessary plus sufficient condition is this. So, again you have the complementary slackness condition. So, that is how what you are trying to say is that whenever g I x bar is strictly less than 0, lambda I must be 0. So, lambda I g I x bar is anyway always 0. So, this condition has to be satisfied, which will immediately guarantee that whenever g I x bar is strictly less than 0, lambda is equal to 0. That would allow you to extend this expression just from I element of I x bar, which is not so nice to look at, I would say slightly uncomfortable to have this summation over the whole range. That is actually, but whenever lambda is not in I x bar, you are putting lambda is 0. So, this is just a nice and compact way of representing this, but this has some other role we will see very soon. And with this, so we have now got an Karush-Kuntakar type necessary and sufficient optimality condition for a convex programming problem, and with this we end today's talk, and we will start describing the notion of the tangent cone from the next lecture. The tangent cone has very silently crept up in the lecture today, but we really did not mention it, but it did its job, and we will talk about tangent cone in the next class. So, thank you, goodbye.